to go to vehicles that like they're always gonna need like, we need some way to fasten this piece to this piece and it has to take up this much space and use this material, so figure it out.
Yeah.
You know, fun little problems.
I think the electric cars are pretty cool.
They're really neat, heavy,
But yeah,
it's, you know, building up infrastructure for them. So is electric gonna be the future? So I know they're popular right now. I think Tesla's done a pretty smart maneuver with, you know, Southern market a while back. Whereas like previously it was like these hybrids, Prius, like it's all about the environment, it's all about you feeling better about yourself and saving the planet. Tesla's like, no, these cars are fun. It's like, there you go, that's gonna sell cars, you
that's
know?
what I see, like, all these electric cars are so fast.
It's all torque.
Yeah, it'd be so fun to just pop in one of those.
Oh, I
Like
would.
the Tesla Roadster.
Let's look at it.
uh,
That little thing, little owl.
What's funny is when the teacher stands right in front of it. I had one teacher last semester. It was like a little bit higher on the desk,
Mhm.
so she'd stand right in front of it and it gave me like a view right up your nose. I was like, man, I wonder if she knows.
Yeah, when you accidentally put a front facing camera.
Why did I
see that? No, thank you.
The Tesla Roadster does like 0 to 60 in less than 2 seconds. And
Yeah,
I'm like, man, that would be like insane to drive.
that's
That's
an
bad.
uncomfortable amount of cheese.
Yeah, I almost
It
think
doesn't
I'd
feel good.
crash and run away if I drove it.
Yeah,
But it'd be fun. I don't know, it's kind of cool.
yeah, I like motors. How much? Thank you.
Okay, let's continue from where we left. Hope your weekend was okay. All right, so let's find the inverse matrix of that. So what we need to do is solution. So what you need to do is we now write A and then we add the I3 there, since this one is a 3 by 3 matrix. And then I3. So this matrix forms now 1 minus 2, 1, 4 minus 7, 3, minus 2, 6, minus 3, and then 1, 0, 0, 0, 1, 0, then 0, 0, 0. So in this case, we want to reduce this matrix here to identity matrix. So if we make this matrix to be identity matrix, then therefore what we get here is the inverse of that matrix.
Good question. We can have all zeros in the identity matrix, or it's gonna be a 0, 0, 1.
Oh, this is good. This is what. Okay, so let's reduce now. Let's reduce. So we reduce just the way we were reducing this. So we reduce this side completely. So in this case, we want to get the new R2, which is R2 minus 4R1, and then new R3 will be R3 plus 2R1 plus 2R1. So 1 minus 2, 1, 1, 0, 0. And then 0, here we get 1, here we get minus 1, get minus 4, here we get 1, and then 0. And then when you reduce this one, we get 0, we get 2 minus 1, 2, and then 0 and 1. 0 and 1. So again, we reduce this. So When we reduce that, then it is the new R3 will be R3 minus 2R2, which will now be 1 minus 2, 1, 1, 0, 0, 0, 1, minus 1, minus 4, 1, 0, and then 0. Here will be 1, 0, and then 1, and then this will be 10, and then this will be minus 2, and then this one will be 1. Then above the pivot position here should make these ones to be zeros. So we get the new R1 will now be R1 minus R3. And then the new R2 will be R2 plus R3 plus R3. So this is 1, then minus 2, 0, and then minus 9, 2 minus 1. The next one is 0. And then we have 1, 0, 6, then minus 1, and then 1, and then 0, 0, and then 1, 10, minus 2, and then 1. So that is what we get. And then finally, we make this one to be 0. So our new R1 again will be R1 plus 2, R2. And what we get is 1, 0, 0, 3, 0, 1, 0, 1, 0, 6, minus 1, and then 1. And then finally 0, 0, 1, 10, minus 2, and 1. 10 minus 2. So that is what we get. So what you can see from here, this is the identity. So therefore, this is the same as now I3, and then what? A inverse. So it's I3 inverse. So since we can find the identity matrix here, then therefore, so A is an invertible matrix. And our A inverse is equals to 3, 0, 1, 6 minus 1, 1, and then 10 minus 2, and 1, 10 minus 2. So that is how you can solve a 3 by 3 inverse matrix. That's how to get the inverse. Okay, now let's come to the next section, which is section 2.3. And this one you're looking at characteristic characterization of invertible matrices. Characterization of invertible matrices. And the first one is the invertible matrix theorem. The invertible matrix theorem. And this one is the theorem that we are going to look at. The theorem. So the following statements are equivalent for an n by n matrix A. So this is an invertible matrix here, and the following are actually equivalent. Number A is an invertible matrix. B, A transpose is an invertible matrix. Number 3, so we can actually name this one as number 1, number 2, and number 3. Number 3, A has exactly n pivot positions. Then number 4, the columns of A are linearly independent. And then number 5, the columns of A span Rn. The columns of A span Rn. So this is what we call the invertible matrix. So all these are equivalent. All these are equivalent. They are equivalent. And we have seen all of it. So we realize that this one is equivalent to this. This is also equivalent. Again, A has exactly n pivot. Is it invertible? Then when we use, we have n pivot positions. One is so if it's also invertible, then the column of A are linear. There is also equivalent. And then this is also this 3 is also equivalent. It's equivalent to 5. So let's try the proof here because I think this theorem is a little bit important. So the proof. 1 is equivalent to 2. 1 is equivalent to 2. If A is an invertible matrix, then from the example that we did, then A transpose is an invertible matrix. Also, 2 is equivalent to 1. So 2 also implies 1. So 2 also implies 1. In that, if A transpose is invertible matrix, then A equals to A transpose is also invertible matrix. So they are related. So then 1 is also equivalent to 3. 1 is equivalent to 3. If A is invertible, then A has exactly n pivot positions. If A is an invertible matrix, then A can be row reduced to identity matrix. If A is invertible, then we can actually row reduce completely to an identity matrix. Also, A has exactly n pivot positions. Has exactly n pivot positions. 3 is also equivalent to 4. So 3 implies 4. 3 also implies 4. So they are equivalent. 3 implies 4. If this A has exactly n pivot positions, if A has exactly n pivot positions, then every column of A has a pivot position. Also, AX, the homogeneous equation AX equals to 0, in that this AX equals to 0 has what? Has trivial solutions. Has trivial solutions. And also, if it has trivial solutions, then the columns of A are linearly independent. The columns of A are linearly independent. And then finally, 3 implies 5. 3 implies 5. In that, if A has exactly n pivot positions, then every row of A has pivot positions. And also the columns of A spans R, and the columns of A spans the whole vector space, which is R. So that theorem is actually related to what we have done since we started this course. We've already done types of this. And then now these are invertible. Any question up to there? Okay, let's look at examples of matrices. How to see whether a matrix is invertible. So let's look at the examples. So let's look at example number 1. So determine whether each matrix is invertible or singular, and then justify the answers. Justify the answer. So the first matrix A, we have our A equals to 1, -5, -4, and then 0, 3, and 4, and then -3, 6, and 1. So to know whether this matrix is invertible or not, then basically we need to follow all this. So we need to follow all this. And then also we need to follow the properties of vector. Vector, check whether it is linearly independent or linearly dependent. Also, we need to use those properties. So in this case, what we can do here is we can reduce this matrix. Since we cannot see the one which is linear combination of the other one, then what you need to do is we can reduce this matrix A. So we need to reduce this matrix A to see whether will give us the pivot positions in each of the rows or each of the columns. So here R3 will now be R3 plus 3 R1. So we have 1 minus 5 minus 4, 0, 3, and 4. And then we will have 0 minus 9 and minus 11. So when we reduce that one, then R3 will be R3 plus 3 R2. And finally, what we get is 1 minus 5 minus 4, 0, 3, and 4, and then 0, 0, and 1. So we can see that we have the pivot position in each of the column there. So in this case, the 3 by 3 matrix A has 3 pivot positions. And so A is invertible. Number B, if we have our B to be equals to 1 minus 5 minus 4, 0, 3, and 4, and then minus 3, 6, and 0. So determine whether this is invertible or singular. So again, we do the same thing, we reduce. So we reduce this matrix, R3, we get R3 plus 3 R1. And when we reduce that, 1 minus 5 minus 4, 0, 3, and 4. And then we have 0, minus 9, and minus 12. So finally, when we reduce this, new R3 will be R3 plus 3 R2, which will give us 1 minus 5 minus 4, 0, 3, 4, and then 0, 0 there. So what you can see from there is the 3 by 3 matrix B has 2 pivot positions. So B is singular. B is singular. Number C. We have this matrix C to be equals to 2, 0, 0, 4 minus 3, 0, minus 1, 5, and 1. It's 5, 1. So what can we do with that? This one is so can do what transpose, right? So we can do the C transpose. So C transpose in this case is equals to 2, 0, 0, 4 minus 3, 0, and then minus 1, 5, and 1. And what can you see from here? C transpose, or we have the pivot position. Using the theorem number 2, where we say A transpose is also invertible, then it means that since the 3 by 3 matrix C transpose has 3 pivot positions, then C transpose is invertible matrix. And so C is invertible matrix. C is invertible matrix. Using the property number 1 and number 2. Any question up to there? Example number D. If we have our D to be equals to 3, 0, 0, minus 5, minus 2, minus 3, 0, and 0, and then 0, 5, 0, and 1, 0, minus 1, 4, 0, and 0. We have that matrix without even doing anything there. So we have 0 vectors, right? We have a 0 vector on the third row. So this is a zero vector here. So using the properties that we had in vectors, if we have a zero vector, then it is what? Linearly dependent. It's linearly dependent. So in that case, without even solving it, this one is what? Linearly dependent. So if it is linearly dependent, then it means it is what? Singular. It is singular. So we can say, since the third column of D is zero vector, then the columns of D are linearly dependent, hence singular matrix. Singular matrix. Singular matrix. Number F. Oh, E, D, E. Oh, okay. We are E. We have this matrix, F, we call this one F equals to 1, 3, 4, and then minus 2, 5, and 3, and then 3 minus 4, and minus 1. 3 minus 4, and minus 1. Without even reducing this, or doing anything, if we look at if we look at this and this and this one, what can we see? So if we add this one and this, you get 4, right? We add this and this, you get 3. Add this and this, you get 4. So it is what? Linear combination. So there is a linear combination there. So 4, 3, and 1 is a linear combination of the two vectors there. So if they are linear, if they are linear, if they are linear combination, then it is what? Linearly dependent. So it is linearly dependent. So we can say, since third column of F is the sum of its first and second columns. The columns of F are linearly dependent, hence F is singular. F is singular. Number F, if we have G to be equals to 3, 2, 4, minus 5, minus 2, 3, minus 4, and 0, minus 6, minus 4, minus 8, and 10, minus 1, 4, minus 2, and 0. And we have that one. So we just look at that. If you look at the first, we look at the first row and the third row there. The first row and the third row. We can actually multiply the first row by -2, and we will get what? The third row, right? So it means that the third row of G is a scalar multiple of the first row, and hence G is linearly dependent. Therefore, then G is singular. Is singular. So if it's a scalar multiple, then it is linearly dependent. Hence, if it's linearly dependent, then it is singular matrix. It's a singular matrix. Okay, any question up to that? Any question? Okay, let's look at theorem 1.2, the theorem. If we let A be an M by N matrix, and B be an N by M matrix, then if A B equals to IM, if A B equals to IM, then B has exactly M pivot positions, and hence M is less or equals to N. M is less or equals to N. Okay, so this is like this. So you have this matrix here, which is A, and this A is M by N. And we have this matrix here, which is B, and this is N by M there. N by M. Then when you multiply this matrix, of course, you get AB. And then this AB will be what? M by N. When you reduce this completely, since it is invertible, if they're invertible, then you get what? Identity matrix, which is what? M by M. So this M, the number of rows in A and the number of columns in B can be equal or less than what? Equal or less than 10. So they can actually. Okay. So I think it's in the textbook. You can look at it. So the proof is just simple, like we can prove simply this like this. If we let the matrix B and then multiply by X to be equals to 0. We let that one to be equals to 0. Then this will give us a trivial solution. Since B is what? Since B is invertible. Since B is invertible. Then if Bx equals to 0, 0 vector, then it means that A, when you multiply by X, A, and then you also do it on the other side, then this is also the same as AB, and then what? X, and which is also giving us what? Which is also giving us 0. Then therefore, if this has trivial solutions which are zeros, then it means that IM of X equals to 0. Then X, since it is a trivial solution, X equals to 0. So that is just a simple proof. Another theorem, 1.3. If A and B are N by N matrices such that AB equals to IN, AB equals to IN, Then both A and B are invertible. Both A and B are invertible. In this case, then A is equals to B inverse, and also B is equals to A inverse. B is equals to and also A is the same as B inverse. So in this sense, since both of them are invertible, then what we can do here is we can just say if we have our AB to be equal to identity matrix, we have our AB to be equal to identity matrix. So when we do the left cancellation, then A inverse A and then B is equals to A inverse identity matrix, right? Right. So since this is invertible, then it means that INB is equals to A inverse IN, and therefore B is equals to A inverse. B is equals to A inverse. The same thing with if you use the left cancellation, the right cancellation, I mean. AB and then B inverse is equals to IN B inverse. Then AIN is equals to IN B inverse. Then A is equals to B inverse. So this. Okay, let's look at invertible transformations. Invertible transformations. Two invertible transformations. Invertible transformations. We still remember the transformation. We write definition 2.1. We say that a transformation which we can put it as T from Rn to Rm, sorry, is invertible transformation if there is a transformation which is S, which is from Rm all the way to Rn. So if it is inverse, so you can transform from let's say from that. So this is a transformation from Rn all the way to Rm, and this can transform back from and this is S from Rm to Rn. I mean that is invertible. So we say that transformation that is invertible if there is a transformation which is S from Rm to Rn, such that T of S, if we put S to be, if we put this one to be Y, is equals to Y. T of Sy is equals to Y. in this case, for any y, which is an element of Rm. This y is here in Rm. And S of T of x is equal to x for x element of Rm if x is in Rm. X is in Rm. So it means that S, if we put this one as T inverse, since this is T and this S we can say is T inverse, then it means T inverse, T and then T inverse is identical to this one, right? The inverse of it, T inverse, and then T is still the same as identity. Still the same as identity. In this case, we say that S is the inverse transformation of T. S is the inverse transformation of T. Let's look at a theorem here. Theorem. If T is from Rn to Rm, is an invertible transformation, then T is 1 to 1 and onto. So that T is actually a bijection. It is 1 to 1 and it is onto. If it is invertible. So here, if we let, so the simple proof is if we let U, the vectors U and V to be in Rn, such that Tu, if we still remember the 1 to 1 is equals to what? T, then U is equals to V. So for this to be 1 to 1, then U is equal to. So this 1 to 1. For this one to be onto, then for any B which is in Rm, then U equals to SB. U equals to SB. So we can use this U equals to SB. This SB is the inverse transformation of T. Then and T of U is equals to T of SB. T of U equals to T of SB. And then we know that T of SB is equals to what? Is equals to B. So therefore, it is an onto. So that means T of U is equals to B. So T is onto and 1 to 1. T is onto. 2.3, another theorem. If the transformation is from Rn to Rm, is an invertible linear transformation, then the inverse transformation S from Rm all the way to Rm is also linear transformation. If T is invertible linear transformation, then its own inverse is also a linear transformation. It's also a linear transformation. So the proof is just similar to this up here. So you can also look at it. And then number 2.4, now theorem 2.4, which is similar to theorem 1.2, 2.4. If we let T to be from Rn all the way to Rn be a linear transformation. With standard matrix A, then T is an invertible transformation. If and only if A is an invertible matrix. In this case, we have n to be equals to m. We have n to be equals to. Basically, if we have the standard matrix in the serial number is E1, E2, E3, up to En. Then if that transformation is from Rn to Rn, basically, since they are standard matrix, then therefore this F always equals to M and should be equals to M. And then the last theorem in this section, 2.5, if we let T to be from Rn all the way to Rn be a linear transformation. If it is now from Rn to Rn is a linear transformation, then number one, T is invertible if and only if T is onto. And then number two, T is invertible if and only if T is 1, 2. And this is basically just like what we just did in our inverse theorem, where we said if we let A, so proof, we let A be the standard matrix of the linear transformation. T, which is n by n matrix, which is n by n matrix. For it to be onto, we said the rows should have pivot position. For it to be 1 to 1, the columns should have pivot position. So T is onto if and only if every row of A has a pivot position. Also, it is onto if and only if A has exactly n pivot positions, since it is an n by n matrix, and then also every column of A has a pivot position. So if every column of A has a pivot position, then it means that T is what? 1, 2, 1. T is 1. So then, if the transformation is from Rn, then T is P, right? If and only if it is onto n 1 to 1 onto n 1 to 1. Any question on that? Okay, if there is no question up to there, then we'll go all the way to section 2.8. And this section 2.8, we'll try to apply what we just learned in section 2.3, this transformation here. So section 2.8, and this one is the subspaces of the whole space, the whole vector space Rn. Rn is actually the vector space, which is the whole space, the whole space. Okay, and the first section that we're going to do in this is the subspaces of the vector space. Subspaces of the vector space. And what we learned here is what we just learned previously. It's just a small section. A small section. So we'll start by defining what a subspace is. So what is this subspace of a vector space? Subspace is just a small space in the whole space. Like if you have a bigger space here, which is a vector space, and all of this is Rn, then we have a small one there. So this small one inside that vector space is a subspace. So the small one has the same properties with the bigger space. So whatever you have inside here, the small, if you pick a small section from the whole space, then its properties of that small space is the same as the properties of the bigger space. So let's look at definition. Let's define this. So a subspace of Rn is a subset. So a subset, which we can name as H of Rn, such that zero vector is in H and U plus V is also in H, and also Cu is also in H for any U V elements of H and C element of grid number. We actually saw this one in the whole space where we say U plus V is an element of what? Rn. That is what we said. So as you can see here, these properties of a small space are just same as properties of the large space. Properties of the large space. So that is the definition of a subspace. So let's look at example. Example number 1 in this case. An example of a subspace is just Rn is a subspace of Rn. The whole space is just the subspace of the whole space. So you can take the whole space. Subspace of the whole space. So this, we can see this one from the properties that we did previously. So this is A, B. The zero vector, the zero, you can put it like that, 0, is a subspace of Rn, where 0 stands for the zero vector E Rn, the zero vector E Rn. Example number 2. If H equals to x1, x2, which is an element of R2, such that x1 plus x2 equals to 1. If, so I'll just say is H, which is this one, a subspace of R2, is this one a subspace of R2? Is it a subspace of R2? We did something like so we just say from the definition that solution, the zero vector of R2 is 0, which is equals to what? 0, 0, 0, which is equals to 0, 0. Then, since x1 equals to 0 and x2 equals to 0, do not satisfy x1 plus x2 to be equals to 1. Do not satisfy that one. Then H is not a subspace. And it is not a subspace. No, of subspace of, we're talking about R2 here. It's not a subspace of R2 because when you put here 0, 0, it is not giving us 0. It's actually giving us 1. And that 1 is not equals to 0. It is not equals to 0. Theorem 1.3, which I will ask you to go look at it in your textbook. Theorem. The span of V1, V2, all the way to BP is a subspace of Rn, where V1, V2, all the way to BP is an element of R. And I think this yeah, reaction. So this part. So this part is actually the linear combination. So they are inverse. So you can go and look at that in your textbook. in textbook. So what you will see is that you will start by checking whether the zero vector is actually there. In that case, the 0 is equals to actually 0 v1 plus 0 v2 plus 0 vp. So the first one is satisfied. And then you can let u1 to be equals to you can just put x1 v1 plus x2 v2 plus xn vn vp or vp, and then you can take v or u2 to be equals to y1 v1 plus like that, and then you just so you will find that the whole of this, the span is actually in R. Okay, now let's look at an example. Example number 3. Determine whether h, which is equals to x1 minus x3, x2 plus x3 minus 1, x1 minus x2 minus 1. Is an element of R3 such that x1, x2, and x3 are real numbers. Real numbers is a subspace of R3. It's a subspace of R3. So determine whether H what. And actually this x1 also R. So determine whether the subspace of R3. So what you can do there is is it giving us the zero vector? Since x1 and x3 and x2, x1, x2, x3 is a real number. So what we can do here, we can actually make a linear system in this case. So what we can do is we can solution here. So we can actually form a linear system whereby this x1 minus x3 will be equals to 0. The next one here is x2 plus x3 equals to, you take the other one, 1 to the other side, and then finally x1 and x2 is equals, you take 1 to the other side, equals to 1. Equals to 1. And then we now write the match equation now. So when we put this one in augmented matrix form, then we get 1, 0, negative 1, and then 0, 0, 1, 1, and 1, 1. This is actually minus negative 1, 0, and 1. So when we reduce this, one, what we get is 1, 0, 0, 1, 0, 1, 0, 0, and then 0, 0, 1, and 1. So when we reduce that completely, that is what you get. In this case, the solution here is x1 equals to 1, x2 equals to 0, and x3 equals to 1. x3 equals to 1. Equals to 1. Now, since it is actually consistent, right? So since we can find the solution here, so it is basically consistent. So it is a subspace of what? It's a subspace of R3. We can also let's set y1 to be equals to bring this x1 to this side equals to x1 minus 1, y2 to be equals to x2, and y3 to be equals to x3 minus 1. Let's set that one to be like that. Then let us go and replace this one up there. So if we replace in this h here, if we replace it here, then what we get is our h equals to y1 is equals to x1 minus 1. So here, then x1 will be y1 plus 1. So y1 plus 1 minus x3 is the same as, we bring this one is the same as y3 plus 1 with that brackets there, comma. And then we have this next one, x2 is the same as y2 plus x3 is the same as y3 plus 1, and then minus 1. And then lastly, x1 is y1 minus 1 minus x2 is y2 minus 1. For y1, y2, y3, element of free log. If we put it like that, then if we solve these, then what you get is y1 minus y3, y2 plus y3, just similar to the one we got there, y1 minus y3 minus y2, so set that y1, y2, y3, element of free log. Then if we write this as what we have been doing, the span, then therefore, this is the same as factoring out y1 here. So y1, and then in this case, y1 here will be 1. This is 0, and this one is what? 1. And then y2, or plus, we can just put plus here. y2 is the same as here is 0, and then here is 1, and then the last one is minus 1, and then plus y3 is equals to negative 1, 1, and then 0. Set that y1, y2, and y3 are elements of real number. And therefore, this is the same as the span of 1, 0, 1, 0, 0, 1, negative 1, and then finally, negative 1, 1, and 0. So since there are 3 vectors there, that means that this is in what? R3. So this is in R3. So it makes parts. So you can actually do it up here, or you can just accept it. Any question after that? Okay, me, I'm tired. So when we meet tomorrow, then we'll come and look at number 2, the column and the null space of matrix. The column space and the null space of matrix. Okay, I'll see you tomorrow.
Yeah.
Back to work.
Yeah. Back to work.